Now, in this section, we'll look at what are called the probability axioms for conditional probabilities. And ultimately, a lot of these are going to look familiar. They're going to be the same things that we covered back in lecture 1 as the general probabilities, but now with the conditions applied to them, inserting a conditional probability and seeing if those same axioms still hold true. And we'll find that most of them do. So again, many of those same axioms of unconditional probabilities apply to conditional probabilities. The first one we'll look at is non-negativity. And we can say first that the probability of A, given that B has already occurred, must be greater than or equal to 0, so long as the probability of B is greater than 0. Now, we've already established that the probability of B must be greater than 0 for the probability of A conditioned on B to be valid. So the question really becomes, can the probability of A intersected with B ever be negative? We know that we have a positive number in the denominator. The only way to make this conditional probability negative would be if the numerator is negative. And the answer is no. If we go back to our basic probability axioms, there is no way for the probability of A intersected with B, the probability of two separate events occurring, to be anything less than 0. Now, it can be 0, but we've said that the probability here must be greater than or equal to 0. So since it can't be negative, this axiom that the probability of A conditioned on another event B must be greater than or equal to 0 as long as the probability of B is greater than 0. Now, normalization, as you may recall, was basically saying that the probability of all events occurring must be equal to 1. And so in this case, we're saying, well, what is the probability of omega, of our universe, occurring if we know that B occurred? Well, the easiest way to look at this is just to plug all of that into our equation for conditional probability. So if we look at this, our A is basically getting replaced by omega in the entire equation. So the probability of omega conditioned on B is the probability of omega intersected with B divided by the probability of B. And for normalization, we, as you may recall from lecture 1, said that this has to be equal to 1. So if we look at this in a little bit more detail, as you may recall from our basic laws of sets, we said that omega intersected with anything, the result of that is just the anything. So we're left with the probability of B in our numerator, and we still have the probability of B in our denominator. Well, that's the probability of B divided by the probability of B, which is equal to 1. So in this case, we've shown that normalization does hold, that the probability of anything occurring or of everything occurring, given that B has already occurred, is just equal to 1. Now, the question becomes, what if we decide that B is just our sample space? Does that work if we replace omega with B? And you would think, well, sure, it does, right? You have some area that is omega, and then you have some event that is B. Well, can I just make my sample space now this area here whenever I'm trying to figure out my probabilities, my conditional probabilities? So for that to be true, we have to say that the probability of B conditioned on B must be equal to 1. So again, the way we'll identify this is just through plugging it into our equation. So for this to be true, we must say that the probability of B intersected with B divided by the probability of B must be equal to 1. Well, looking at the left-hand side, B intersected with itself is just the probability of B. So we have the probability of B divided by the probability of B, which looks really similar to what we had above. Well, that's equal to 1. So in this case, we have that the probability of B conditioned on B is in fact equal to 1. So the B, event B, can really be considered our new sample space. Now, the last axiom that we'll look at in this section is that of additivity for conditional probabilities. And you may recall from lecture 1 that we said that if we have a probability of A unioned with B, that probability A union B was equal to the probability of A plus the probability of B only if the intersection of A and B was equal to the empty set. And we're going to look at virtually the same formula here. We're just going to put this in terms of conditions and make sure that it holds. So in this case, we have that if the intersection of A and C now is equal to the empty set, then the probability of A unioned with C, conditioned on the fact that B has already occurred, should be equal to the probability of A conditioned on B plus the probability of B conditioned on C. Now, again, we're assuming these are disjoint sets, and you can see that represented here in the picture that there is no area that is common to A and C, but they both have an area common to B, our common event. So in this situation, the best way to look at this is to, again, just plug it into our equation for conditional probability. So our A in this case is really just going to be A unioned with C. Now, to do this, we're going to say first that this probability of A union C conditioned on B should be equal to, again, just by plugging it into the formula, equal to the probability of A unioned with C intersected with B divided by the probability of B, which should just follow from this equation. Now, by the distributive property, we can say that this is equal to the probability of A intersected with B unioned with C intersected with B. And again, all of that over the probability of B. Now, what we have on top is just our basic additivity axiom. We don't have any conditions. We just have two things that are unioned together, that A intersected with B is this area here, and C intersected with B is this area here, which by the definition of A and C being disjoint, this intersection with B also must be disjoint. So what we can say now from our basic additivity axiom is that that equation is equal to the probability of A intersected with B plus the probability of C intersected with B, again, all over the probability of B. And if we split that out, what we're left with now is the probability of A intersected with B over the probability of B, which should be very familiar. That's our definition of a conditional probability. So the left-hand side of this we can say is just equal to the probability of A conditioned on B. And then we're going to have a plus in the middle. And on the right-hand side here, we have the probability of C intersected with B divided by the probability of B, which is just the probability of C conditioned on B. And so in this case, we have the probability of C conditioned on B, which in theory, this now matches our initial definition. So we can say that if A and C are disjoint, then the probability of A unioned with C, then conditioned on B, is equal to the probability of A conditioned on B plus the probability of C conditioned on B.